Good afternoon, everyone. My name is Dezhan, and I belong to Team 14. Today, I'm gonna do my midterm assignment presentation. The monthly time series that I chose is Y5, which is U.S. natural gas total consumption. The period is from 2001 January to 2022 December. Now let's come to the first part. The first part is time series description. And we can see that there is a dynamics plot of Y5. In this graph, we can see that there is steadily rising trend in US natural gas consumption from 2000 to 2022. And there's a clear seasonal spikes, which is likely driven by heating demand. The increasing baseline suggests that the US natural gas is becoming more widely used across sectors beyond just seasonal heating. And here is a one-year dynamics of Y5 in 2022. We can see that in 2022, US natural gas total consumption showed a clear seasonal pattern. It peaks in January and December due to winter heating demand. And the consumption was lowest during the spring and early fall, with a relatively steady plateau in summer months, which is likely driven by electricity generation. And here's the seasonality plot. This seasonal plot highlights the strong seasonality of US natural gas consumption throughout the year. We can see that the consumption is highest in winter months, just like in January, February, and December, with averages above 2.5 to 2.8 million mmCF. And it was lowest in late spring and summer months, just from April to September, with means closer to 1.6 to 1.8 million mmCF. We can see that the consistent peaks and bottoms confirm a strong seasonal cycle driven by heating demand in colder months. And here is the descriptive statistics of Y5. We can see that the mean value of the data is above 2 million. And the histogram shows a slightly right-skewed unimodal distribution with most value between 1.6 and 2.6 million mmCF. I think that this reflects a strong seasonal variation. Higher values correspond to winter peaks. And here is the autocorrelation function and partial autocorrelation function detect. Based on the autocorrelation and partial autocorrelation function patterns, we can see that the partial autocorrelation function generally cuts off sharply after leg 1, while the autocorrelation function decays gradually and remains significant for many legs. I think that this probably suggests an armor 1Q structure, probably with armor 1.1 or armor 1.2 being good initial candidates, but I cannot identify a specific value of Q based on the current info. Additionally, and the presence of strong autocorrelation spikes at legs like 12, 24, and 36 indicates clear seasonality. And next part is about unit root test. I have done all 3 models of unit root test, including constant only and trend and intercept, and no exogenous variable. All 3 models just show the same result, which is Y5 has just exactly 1 unit root. So I decided to work with the first difference of Y5, which is dy5. Here is the plot of dy5. We can see that the first difference of Y5 somehow effectively eliminates the unit root and transforming the series into a mean reverting and stationary process suitable for just time series modeling. I think that it also captures the short-term, month-to-month changes in natural gas consumption. And now let's come to the forecasting part. The forecasting part consists of 5 parts, and the first part is the determination of training and testing period. My decision is that the training period is from 2001 January to 2021 December, and the testing period is from 2022 January to 2022 December, which just a month of testing, a 12 months testing period. And in my opinion, the training sample covers 21 full years of monthly data. It provides 252 observations. I think this long span captures the multiple seasonal cycles and several economic shocks. For instance, the 2008 crisis, also the pandemic in 2020. Such coverage ensures the model learns both the trend and the recurring seasonal behavior accurately. And the testing period provides a complete annual cycle, enabling the evaluation of the model's seasonal forecast accuracy. And it also directly measures the predictive performance across all seasons. And here's top 20 models for the training period that I estimate according to the AIC criteria. And according to AIC criteria, here's the top 10 models. And I can see that the top one model of this ARMA forecasting is 10110. I include the top 10 models and record their RMSE, and here's the all the RMSE for the testing period of all top 10 models, and we can see that based on the smallest RMSE, the best model is still ARIMA 10110, and so I just use this model to do estimation. We can see that this is a quite great forecasting. According to the RMSE, this one is absolutely the best model. And I think that overall, the model ARIMA 10110 provides an accurate and stable forecast of US natural gas consumption for 2022, with RMSE representing less than only 7%. Actually, it's 6.77% of the mean level. So I think this really great, and the result suggests that the fitted model effectively captures both the trend and seasonality of the series. Now I use the best RMSE model, ARIMA 10110, to estimate it again based on all available data. And here is the model estimate. And I use that model to do a real forecast for 2023 January to 2023 December. And we can see that the 12 months ahead forecast for 2023 shows a realistic and stable seasonal pattern, with consumption decreasing in warmer months and rising toward winter. I think this smooth cyclical behavior suggests that the model provides reliable short-term forecasts and successfully capturing the seasonality and the trend components of US natural gas demand. That's the end of my project, and thanks for your listening. And if there are any questions or comments on my project,